Okay, so the talk that I'm going to give today is a little bit different from what you've seen today. Is it working? Yeah. So I will talk about the development of density functionals in DFT using neural networks, and why we need to develop new functionals, because we know there are many. So I'll start from the very beginning. Okay, since it's late and you're all very tired, please feel free to interrupt me at any time if things are not clear. Okay, so let's start from the very beginning, from the golden age of quantum mechanics. So here it's the first 40 years of the development of quantum mechanics. So from the very first publication by Heisenberg, it's in 1925, in which he proposed a very different approach to the study of electrons. So now particles are described in terms of probability, and we use matrix mechanics. Then the development by Schrödinger of the wave function, so the description of a particle, its evolution in time by using wave functions. And then Dirac, that was only 24 at that time, read the paper by Heisenberg and said, I can do better. So together they worked to create a formalism using commutators. They put together the concept of probability and the evolution of a particle as a wave. So I'm not going to go into the detail, but you see that then we have the definition of the wave function as an antisymmetric product of one electron orbitals, the Archiba approach, in which electrons move in a mean field, so the mean field approach. So the electron gas of fermions, the Thomas Fermi model, which is very, very old. And following that, Dirac proposes LDA, so the local density approximation that is born way before density functional theory. Okay, so now so how many of you know the theorems of Weinberg and Kohn? Okay, so anyone wants to say the first theorem? Any volunteer? Be careful when you raise your hand. No volunteers? Okay. So Weinberg and Kohn, they established a one-to-one correspondence between the density and the external potential. So the density that determines univocally the density of the system. And the second theorem, it states that there exists a universal energy functional of the density, and the ground state energy is obtained by minimizing this functional, because it's a function of a function, with respect to the density. Okay, so this means that the ground state electron density determines all the properties of your system. So we know that the functional exists, but nobody knows the shape of this functional. Who knows about the quantum equations? Okay, what does Kohn and Champ propose? Any volunteers to say? Without reading? Okay, so now we have a practical way of solving the Schrödinger equation in a much more practical way, tractable way. So we use an independent particle approach. So now we have an independent particle. That's the mean field, okay? An effective potential, this mean is an effective potential that is given by this, the sum of this term, the external potential, which is given by the position of the ions, the Coulomb term, and the exchange and correlation. So this independent particle sees a mean field where the many body terms are included in this term here. So basically they introduced the idea of replacing the complex many-body system, as proposed by Slater, with a fictitious system, where we put all the things that we don't know in this term, the exchange and correlation functional. Okay, so the quantum equations are a huge advantage to solve the density functional theory, so we call it quantum density functional theory. And the way to obtain the total energy is to start from the gas density. So we write the effective potential by using this density in the Coulomb term and the exchange and correlation term. So we have our effective eigenvalue problem. We diagonalize it. We have the eigenfunctions. From the eigenfunctions, we obtain the density, going back to Kohn-Sham approach. Is the density converged with respect to our guess? Yes or no? If it is converged, then we use that density to compute the total energy. Otherwise, we update the density by mixing the previous one and some new density and keep going until we are converged. So as I said before, from Hohenberg and Kohn, we know that this functional exists, but nobody knows its exact shape. We know that it depends on the density, and there are many approximations to it. Density gradients, etc., that I'm going to explain later. So building good approximation for this term represents the huge effort in the community, and it's at the core of the DFT developments of the last many years. So here I'm continuing the diagram that I started before, so the golden age of quantum mechanics. So now we have the Hohenberg and Kohn theorems, Kohn-Sham equations, so Kohn-Sham density functional theory. Here it's LDA, as I said before, we use the homogeneous electron gas to parameterize this term. So now the exchange and correlation energy is the integral in volume of the exchange and correlation energy density, okay? This is an energy density. We have the definition, development of the GGA, generalized gradient approximation, where now the exchange and correlation energy depends on the density and its gradient. Sorry, there is a mistake. Other functionals developed. So I'm going through chronological order, okay? So, okay, exchange and correlation functional depends on this. Now we have the meta GGA, 1988. Meta GGA, it's everything that goes after GGA, beyond GGA. So most approaches use the kinetic energy. Other functionals developed, other parameterization of the meta GGA. Beckett proposed hybrid in which we mix here some amount of exact exchange. For example, the first function to be proposed is B3-LEAP, in which we have a fraction of LDA for the exchange, with the LDA correlation, and a fraction of Hartree-Fock, which is written here. Okay, so this is called, I put it the other way around, but it's usually called the Jacob's ladder for density functionals. So here I'm showing Jacob's ladder from the cathedral, I think it's in Bath, in the UK, which you see the angels that climb to the heaven. So what is the Jacob's ladder? Jacob's ladder is a concept that was proposed by Perdue and Smith. As you remember, Perdue is one of the fathers of density functional theory. So it makes reference to Jacob in the Old Testament, in the Genesis, who has a dream, and he dreams of God, and the God that gives several promises of numerous offspring and the promised land. And he tries to reach God climbing this ladder. So, okay, so the concept of Jacob's ladder is used in many other fields, not only in density functional theory, it's used in literature, in climbing plans, and I forgot, in literature I said. And this is the first paper in which Perdue proposed this Jacob's ladder. So it's from the conference proceeding. And you see here, as the ladder goes up to heaven, you have LDA, and then as you add ingredients to your exchange and correlation energy density, you go towards heaven, which is the chemical accuracy. Okay, so, right, so there is a huge effort today in the community to develop new exchange and correlation functions. But what are the directions and what are the strategies that people are using or following? So you probably heard about the adiabatic connection, fluctuation dissipation theorem. It's a formulation which you go from the fully interacting system to the non-interacting system, and this approach is used to derive to parameterize hybrids and double hybrids. Then we have constraint satisfaction, so our function needs to fulfill several exact conditions. This is the case of LDA, PBA, or SCAN, or even Koopman's compliant functional, in which the orbital energy needs to fulfill the conditions of ionization potential and electron affinity. Then we have objective reactive fitting, in which our functionals need to reproduce many properties that we know from, for example, databases. And this is the strategy, the concept used mostly by Trular in Minnesota for the Minnesota functionals. All the functionals that you see that start with M, these are the Minnesota functionals. Some of them are meta-GGA, others are double hybrid, etc. Highly parameterized functionals. Okay, so where does machine learning appear in all this history? Well, so I certainly not exhaustive in this, but it's true that I'm going to present a view of this field which is biased, as everybody does, right? We give our own interpretation. So I like to start from the toy model presented by Burke, who really provided a huge contribution to this field, in which he, for very simple systems, he creates a correspondence between the kinetic energy and the density. A very nice paper, 2017, in which he creates a model, a simple model, which replaces the Concham equation, so you don't have the self-consistent field anymore, and you have a map between the density and the potential, so the Hohenberg and Cohen map that we saw at the beginning. More technical aspects in which the functional is developed is designed in terms of convolutional neural network, and I like to present the work of Nagai, which I'm going to describe in more detail later, which is the first attempt to define an exchange and correlation functional using machine learning. So the directly exchange and correlation functional. So machine learning appears in the family that I described before as the objective reactive fitting strategy. So we were really fitting our functional to reproduce some well-given properties in the same philosophy as the Minnesota functionals. So how do we get weights and biases when we use neural networks? So I'm going to show this in the detail. So we need to have a loss function that's quick to compute, that represent the physical and chemical property of our system, and it should define an order and equivalence relation in the solution, having a global minimum on the model. Here's an example on the total energy, for example. Okay, so this is the first work that I'd like to discuss, even though it's not the first that was published, in which the exchange and correlation energy is defined by density, is defined by a neural network, and the quantity that we fit we give to our neural network are the density, the spin polarization, the reduced density gradients, and the kinetic energy. So we are in the realm of meta-GGA, and this functional was trained on very simple molecules, on atomization energies, experimental atomization energy, and high-level coupled cluster electronic density. So this is a proof of concept to show that this is the functional, that you can develop a functional that is the best performer, you see many other families, for densities, for total energies, for energy barriers, and for atomization energies. Okay, interesting work. Now I'd like to talk about the functional developed by Google, DM29 from DeepMind. Okay, so question for you, so that I make sure that you don't fall asleep. So does anybody know what are the major deficiencies of density functional theory? So we know that it's not perfect. We don't have the perfect functional, okay? We have approximation to it, and these approximations don't work well. Do we know why they don't work well most of the cases? Students, please, raise your hand. Yep.
Because the guess for the exchange correlation function is
Yes.
fictitious.
What's wrong with the exchange and correlation functional?
Well, you don't know what form it takes.
Yeah, but we do have approximations, right? So what's the problem with the most standard approximations?
Okay, well, if you approximate, you lose that out on information.
Yeah, but there is one specific thing that
So you don't know where all the other electrons are actually, so that like if you want to precisely calculate the probability of one electron, you need to know where all the other electrons are at the same time. You don't know that, so
but the framework of Hohenberg and Cohen, they say okay, and then Concham, they say you use a fictitious system, but as long as you have the exact density of this fictitious system, you have the exact properties of the fictitious system, so the exact properties of the system. So the density of this fictitious system is the true density. Okay, this is what they say. So if we had the exact function, we would have the exact density. No problem, but what you're saying, it's already included. But there is an issue in, yes?
About self-interaction error?
Yes, yes.
Because the exact exchange usually removes exactly the double counting in ij, I plus j.
Yes.
But we're approximating the exchange also.
Yes. Exactly. So the problem is that, sorry, I should not have done this going back, but so the thing is that why it's called self-interaction error. When you write down this equation for one electron, this term does not cancel out with this term. So we have that one electron interacts with itself. And this is not true in Hartree-Fock, in which the two terms cancel with each other. So this is the self-interaction error that is responsible for many errors in DFT, such as, you there, since you know? For example, bang up, the localization errors, etc.
The nonlinearity of having results.
Right, exactly. So this is exactly what this paper wants to do, and this is why, as I said before, I'm a biased person, and so I'm going to show you this paper that I like very much, because what they want to do is they say, okay, we know what the major deficiencies of DFT are, so let's use machine learning to remove them. So, okay, so this self-interaction error is also called charge delocalization error. So the charge delocalization is a consequence of the self-interaction error. So what it happens, Perdue and Zunger, they demonstrated that for exact DFT, when you go from integer charges, you should have a linear interpolation of the energy, pairwise linearity, which none of the functionals that we know have. So they have this, it's small, but usually they have big bowing. So this can be illustrated in the case of H2+. So in the stretching of H2+. So H2+ has 2 protons and 1 electron. Okay? So when you stretch, you have 1 electron that has to localize somewhere. So what we find in DFT, that you have half an electron that localizes one proton and half an electron on the other proton. And because of this energy bowing, you find that this configuration is enormously stabilized with respect to the bound molecule. And this is a way to illustrate that this error is not just a fictitious error, but really occurs in systems, in everyday chemistry. Very good. They want to remove this error, and so they fit their neural network to reproduce this linearity. Second thing, fractional spin. Huge error in DFT too. So what happens is that in DFT, when you have a system with fractional, so as long as the total spin is maintained, the different solutions that the total spin the same are degenerate. Okay, so if you have two atoms, so in this configuration here, for example, now we have the H2 molecule. So we have spin up here, spin down here, and the fractional, so we have half of a proton in one and half of the proton in the two. So we have two fractional spins. So the exact DFT says that all this configuration, because they have the same total spin, you see, they should be the same, but they are not. And so because here we are localizing the spins, we are breaking the symmetry, we are localizing the spin. We have one atom that has half spin up and half spin down, and the other hydrogen atom that has half spin up and half spin down. This solution is not equivalent to the solution in which each atom has its own spin. Then you have this error here. Okay, so this is called static correlation error, and whenever you see that functionals try to recover the flat plane condition, it means that they try to recover at the same time this linearity here and this linearity here. And this is what they try to do in this work. Okay, so they have the huge neural network, and they have a lot of different features that they give to the neural network to be optimized. The density, the gradients for spin up, the gradient for spin down, the kinetic energy, and the Hartree-Fock energy density. So this is defined point-wise. So it's huge. The size and the training of this thing is huge. They train on these exact conditions, see, half of a spin, and on many 1,000, 1,100 reactions. And they say, so I'm not going to show the results, but they have tables in which they show that they are the best performers for the QM dataset and another dataset of chemical reaction where energy is computed with a higher level of theory, like a couple cluster. Okay, so this was a very interesting work, but it was, because of its impact, it was shown that he had a lot of deficiencies. So the first was a comment on Science. So the paper, I think it was in Nature. And they say, okay, so the authors say, it's not true that your functional performs better than the others because you add the fractional spin and fractional charge. But it performs better because when you introduce the fractional spin and the fractional charge, you're introducing systems in the training set that overlap with the system in your testing set. So what they say is that, so I had written the piece which was written very nicely. They say, so this situation highlights the difference between testing a model in physics and in machine learning. In physics, the performance of a model on a test dataset shows how well it represents reality. On the contrary, in machine learning, where a model is trained on some dataset, training set, its performance on a test dataset shows the model's ability to generalize, that is, to understand versus to memorize. Because the machine learning models generally tend to be better at memorizing it, it is crucial to test on systems unlike those used to train it, which they claim they do. Otherwise, the so-called data leakage can artificially inflate the performance of the metric. So this is what they're saying. Your function is better because you are using the same data to train and to test. So another work on DeepMind 21 functional. So these authors demonstrate that it's very unstable functional. So when you want to do the conversion of the self-consistent for transition metal, it's really hard. It's really hard, and sometimes you cannot convert. It just fluctuates between a cycle and the next. Okay, another very nice work, very elegant, that I like very much, is defining functional using symbolic links. So now we are not training a neural network, The authors are trained mathematical objects. They are functions, okay, that they combine with different operations, sum, products, exponential, and they train it on different data sets. So the first thing they do is, let's see if this thing works. So we train our symbolic functional, and we want to reproduce something that is known. So let's train it on a bunch of data coming from the B89, 87. And what they do is that they use genetic algorithms to minimize the error, and they find a function that is exactly B87. That is the proof of concept. And then they go, and then they just develop a new, more complex one that is very good functional. Okay. First part, questions? Then I'll answer the question, why am I telling you all this?
I don't think I'm 100% clear about what trick the DM21 model did.
Sorry.
I'm not 100% clear about what is the trick of the DM21 model.
What are the tricks? What do you mean the tricks? The problems?
Not the problem, what they did so that they fixed the fractional electron problem.
Oh, so they, okay, so they impose this linearity between here and here for very simple ions, noble gas ions. Then it's a complex problem because you need to go from the density to the orbitals, so they need to do some inversion scheme to do that. So it's a nice effort, and it's well documented, and it's, I mean, rigorously done. Okay. So it's convincing. It's just that the functional at the end doesn't work. Okay. Other questions? Yeah.
How is the density represented here? Is it like on the normal DFT grid or in the basis step coefficients, or what is the actual input to the model?
So here, the density of the molecules is never touched because they use the assumption that, so this is a condition on the energy, okay? Not on the density. So their working hypothesis. Sorry?
You just learn a correction on the energy, but you don't.
It just changed the energy. So they take the B3 leap density, and their assumption is that in the true functional, B3 leap is the global minimum. So also the second order derivative, so not only your functional passes by B3 leap, but also it's a minimum for each configuration. So the density is never touched. Sorry, yeah.
On the ultimate slide, he showed where there was the in the I guess this is just they used a linear like normal regression model. Like.
No, they use genetic algorithms.
Okay, I don't know.
So you don't use gradients, you just do derivative, you just explore your solution space. I'm going to show you some examples later of what the genetic algorithm is.
But it's not just like linear regression.
No.
It's non-linear ML model, right?
Okay, it's non-linear, yeah. It's a genetic approach, yeah. Okay, because it's a school on material science, I'm going to talk about some materials. I saw some posters about metal organic frameworks, which is the family of materials that I'm most interested in. So why do I study metal organic frameworks? Because I'm interested in developing new strategies for carbon capture. So we know there are many different strategies that are being studied, so ionic liquids, conventional chemical absorption method called the wet scrubbing with the monoethanolamine, that it's the only strategy that we can deploy in large scale, but it's too expensive to be deployed, and that's why we develop carbon capture strategies. And so, yeah, I'm interested in metal organic frameworks. So these materials are, am I too basic with this, or go fast? It's fine, okay. Metal organic frameworks are three-dimensional porous materials composed by a metal ion and an organic ligand, and they give rise to these three-dimensional porous materials. So to me, that I've been working on these materials for 15 years, 10 years, it's crazy to see that it's very long history of metal organic frameworks. At the beginning, they were really struggling to get these materials with permanent porosity. And the first one that was synthesized by Omar Yagi in 1998, and there was, I didn't put the sentence, but so at the Gordon conference, they were talking about these porous materials, and they were saying, would we ever be capable of synthesizing such materials with permanent porosity? And the first MOF came 8 years later. And today, there exist around 77,000 MOFs in the literature. There's been a huge explosion of this field. So you see that there are many different topologies of pores with local chemistry, etc. They're very tunable because you can change the chemistry. So I'm myself working on luminescent MOFs, photoresponsive MOFs that you excite with light and they change the conformation. Spin crossover MOFs that I'm going to talk about after. And due to the fact that they have this huge chemical tunability and that they're porous, they're mostly studied for catalysis and gas adsorption application. Does anybody know what an adsorption isotherm is? Yeah. Okay. Who raised the hand? You. What does it measure? What can we get from this? Yes, so a material, in order to be interesting for gas adsorption or capture, you need to capture a lot of it, right, if you want it to be efficient. So you have the partial pressure of the gas and the amount of gas uptaken. Okay, so if we want to have a material that is very good for carbon capture, it means that we need to be able to capture it, but because we need to store it underground, we need to be able to capture it and release it easily, right? How is gas released normally when you absorb it? Who's speaking?
Temperature, heating it up.
Who's speaking? You, okay, sorry. Yes, you can heat it, you can pressurize it, you can apply light, there are many strategies. Yeah, so the thing is that pressure is the same thing, but if you heat it, so imagine that you absorb gas. So imagine that you have a power plant. So your flue gas, you do the combustion, you create electricity. The flue gas, it's what temperature? What temperature is the flue gas? You don't know. Temperature is the flue gas. Room temperature, okay? After the combustion, you get out the gas, and it's at room temperature. Let's say that room temperature, it's low temperature for us. We absorb here, okay? So usually, the flue gas is at 1 bar. We have around 20% of CO2. So here we have 0.2 bar, and here what we absorb. We want to release the gas. We heat, and we are here, okay? We are at higher temperature and higher pressure. And this is called the working capacity. This is how much gas I capture and release, capture and release, capture and release. At each cycle, I want to do many, many times. So what we need to do is need to have this very big. But what's important is not that this is very big, is that the parasitic energy is low, which is the energy required to desorb and pressurize a kilogram of CO2, which is related to this. So the parasitic energy is very high because the cost to heat the material and remove it would increase the cost of electricity by 40% if we use the materials that we know. That's why we don't have carbon capture. Okay, so my research on materials aims at having very large working capacities, but without having to heat, right? So in my group, we are following different strategies. One strategy is to use light. So imagine you have visible light, you use filters, and you switch the wavelengths, and you capture, release, capture, release. This is one field of research that I'm not going to talk to you today. Another one is using another electronic transition. Okay. Does anybody know what spin crossover is? Nobody. Okay. Spin crossover are materials that, okay, this is the electronic structure of a ligand field of iron. We have the T2G, which are the orbitals that point towards the ligand, and the T2G, which are the orbitals that are non-bonding. Spin crossover materials undergo a spin crossover, spin transition from low spin to high spin. So what we did some time ago, we demonstrated that when if you have an open metal here, and you have CO2 bound, if you induce a transition from this to this, what you have is that because this is an orbital that is binding this atom, it's an anti-bonding orbital, meaning that if you populate it, you break the bond. If you induce a transition from this to this, you are occupying a non-bonding orbital, so you break the bond. So we demonstrate that you can decrease the binding energy by 40%. So you can imagine to absorb at low spin, so you have strong absorption. You heat your materials just a little bit, so you don't want to heat it. You don't want this transition to be at 1000 Kelvin, because then you can't use it. You want this transition to be at maybe 10 degrees above your flue gas temperature, and then you go to high spin, which results in a weaker binding, and so desorption of the gas.
One thing, you can
Yep.
principle have the spin crossover if you apply a magnetic field. Did you explore that?
No, we did not. You can do with the magnetic field, you can do with light, yes. Yeah. The difficulty with the magnetic field, yes, but with the difficulty with light and temperature is the same, because you can demonstrate that when you excite it, your metastable state is proportional to the difference in energy, so you don't gain much. Okay, that's very interesting. So we need to find materials, and this is another area of my research that I'm not going to talk to you today. We need to find the materials that has a very strong absorption with gas at low spin, and that undergoes this transition at specific temperature, as I said, right above room temperature. So we need to solve this equation. We need to compute the delta G, the reaction, and we need to compute all these terms, delta E vibe, and the entropy. These terms are relatively easy to compute with modern electronic structure methods. Vibrational modes, harmonic approximations, easy. They are accurate. Delta E, very difficult. Very difficult for any ab initio method, including couple cluster. Okay, why is it so difficult? I'm going to show it numerically, and then I'll try to explain you why it's so difficult. So here it's the adiabatic energy difference. So let me check the time. 45 minutes. Huh?
Yeah, 20 minutes.
20?
Yeah, because we started. No, sorry.
No, we started at 4.
Yeah, we started. Relax.
So do you need a pause? No, okay. So I want so I will show you numerically that it is very difficult to have an accurate description of this. So, sorry, but then I can't. So you see, so okay, I have this octahedral complex, okay? So we have the EG, the EG and T2G orbitals, as I said before, and we have different ligands. From left to right, we go to weak to strong ligand field. When we have strong ligand field, the interaction between the ion and the ligand is very strong. And so we open the gap between the T2G and the EG T2G. So the delta E, high spin minus low spin. This is the adiabatic energy difference. High spin minus low spin energy increases. Here I'm showing how different functionals perform to compute this delta E. And you see, well, CASPT2 corrected coupled cluster, it's the method that we use as a reference. Is anybody familiar with the CASPT2 approach? No? So CASPT2, it's the state-of-the-art method for electronic correlations. It captures dynamic correlations, like fluctuation of density, and static correlations, like multi-configurational approaches, solutions. So it's corrected by coupled cluster because the dynamic correlations are not always well treated, are treated with perturbation theory. So it's been demonstrated that this is the most accurate approach to compute such properties. And this is what we computed as a reference. And these are different functionals. You see that the deviation is huge, 4 eV. If you have 4 eV difference, it means that your transition temperature for spin crossover is 10,000 Kelvin away from what you want. So it's too much. You need to have accurate delta E of the order 0.1, 0.2 maximum. Same thing for method GGA, a little bit smaller than there, but also very large errors. Okay, so different functionals yield very different results. It's true that hybrids, you can tune the amount of exact exchange to tune the delta E. The problem is that you don't know. You need to have your reference first. So if you have your reference, then you don't need to compute it. Useless. Okay, so the question that we ask ourselves is, can we develop an exchange and correlation functional that predict accurate values for delta E? I don't know if I want to explain this. Is anybody familiar with DFT plus U? Okay, so okay, I will try to be quick and pedagogical. So, okay, so the DFT plus U approach, it's a semi-empirical approach in which we add to DFT a term that's called the Hubbard term, that it's borrowed from the Hubbard model, right, in which we have a non-sign Coulomb term and the kinetic term, and by tuning the parameters here, we can open the gap. We can describe the physics of multi-insulator. Okay, so the same thing, what we do in DFT, we introduce a potential, okay? Don't look at the shape of the potential. Just keep in mind that what you do with the U potential is that depending on the shape of your orbitals, DFT orbitals, on the way you project the DFT orbital to some basis, you move them up or down. This potential can be positive or negative. So you can choose this term, parameterize this term in many different ways, and the way it acts on the quantum quantum eigenvalues is defined by this formula here and this formula here. So basically what your formula is saying is that imagine that you want to, you have problems with the d orbitals that are localized, so the dynamic correlations are not well treated in DFT. What we can do is that by applying this potential, we can move some orbitals, the orbitals up, some others down, and we can open the gap. And this is what DFT plus U does. Was it clear? No? Yeah. So what it also does, DFT plus U, is that it tries to restore this piecewise linearity that I said before. So he has very rigorous approach, and the formalism that the formalism from which this originates is very similar to the Hartree-Fock potential. It's a very rigorous approach. The question is that there are approximations, like the way you choose the orbitals to which you apply your U, and the choice of U. Another topic that I don't want to treat today. But DFT plus U has a huge problem. Does anybody know what DFT U's problem is? U, yes. Choosing U, but not only. That's a minor problem. The huge problem with DFT plus U is that you have this term. This term is always positive in the energy. It means that you are always destabilizing your system by this quantity. The thing is that in many chemistry situations, current chemistry situations, this term does not reflect the true chemistry. So when you apply it to multi-insulator, it does. You can open the gap, stabilize, have a larger term for the metal. So you destabilize the metal and you stabilize the insulator. But when you have this in DFT, sometimes it's not clear why in one configuration it's higher, in another configuration it's lower. It's a bit arbitrary. And this is what we discovered and what we tried to treat with Lorenzo, was a former PhD, brilliant student in my group. So if you use PB plus U, you see that now your adiabatic energy difference as a function of the ligand field is flat. So you completely lose the chemistry of your system. And the reason why is that this term here is progressively larger as you increase the ligand field. So you're destabilizing more and more the low spin configuration as you increase the ligand field. And so this does not reflect your chemistry anymore. You don't have the true trend. You don't even have the true trend. And this is the reason why you have this is because of the way these things are written. These things are projection of your quantum density onto some local basis set. And these projections are more fractional when you have strong binding, strong covalent bonds. So basically what you're doing is that you are destabilizing strong covalent bonds. But we don't care about this here. So we completely miss what's going on. And this is why also, for those of you doing catalysis, there's a nice article of a professor, Nuria Lopez, in Tarragona, I think, in which she says, don't use DFT plus U if you want to study chemical reactions. And she numerically shows why. She numerically shows that in your transition state, your energy is off due to this term. And this is the reason why, because this term doesn't reflect your chemistry anymore. Okay, so what Lorenzo did is that, okay, the energy, the Hubbard energy is wrong, is very wrong, but the Hubbard density is very good. And we demonstrate, we compared pointwise the electronic density, and we showed that the density of diff plus U resembles more the electronic density of CAS-PT2 than PB. And because our working hypothesis is that PB is a good energy functional. So what we did is that we did a non-self-consistent approach in which we take the DFT plus U density, and then we evaluate the total energy by using a functional that is not a number function, like PB. So we compute the PB density, use PB to compute the energy, and this is why we call the density-corrected scheme, and this is our energy. So the density-corrected scheme works well, and this shows that this problem is mainly a density-driven error problem, meaning that the density is wrong. The DFT, the PB gives you the wrong density. When you correct the density with the PB plus U, you get the right density, but you can still use the PB energy functional. Okay. Right. But there is a problem. It's a non-self-consistent approach. So why having a non-self-consistent approach is a problem? If you want to study materials and properties. Yeah?
Well, if it's self-consistent, then could you then just compensate with many iterations and it should converge in the end? But if it's not, then you cannot apply more computing power and get closer. You just have what you have.
Yeah, but you're happy because this gives you the right energy, so you're happy. But still you cannot do the self-consistent approach. It means that your eigenfunctions, your solution is not an eigenfunction of your Hamiltonian. What's the consequence of this? The consequence is that you cannot apply the Hellman-Feynman theorem, so you cannot do dynamics, for example. So you cannot compute molecular dynamics. That's why we decided to develop a neural network, use neural networks to develop new functionals, to a full self-consistent approach to describe adiabatic energy difference. Okay, so I forgot to tell you, so I showed you numerically why DFT is wrong in getting the energy difference between two spin states, but I forgot to tell you, so I showed you that this is the case, but I didn't tell you why. Why is DFT so wrong? But even couple cluster, why is couple cluster so wrong to describe these adiabatic energy differences? There's a difference between two spin states. Yes?
From DFT you get ground states.
Okay, fair enough, yeah.
And if you have a transition to an excited state, then maybe it's not enough to get the ground state.
Yeah, so you are sure that you are right just in the ground state for DFT, yes. But we can compute like many total energy differences in DFT that you're still not in the ground state, you have different configurations, but those energy make sense. They have a true physical meaning and they're correct. But this is, they're off. Their EV is off. Well, I don't have the answer. Nobody has the answer, but I can tell you what I think is the reason. So what I think is the reason is that when you do the difference between two different spin states, you have very different type of electronic correlations. Static and dynamic change a lot. We can know there are arguments in chemistry in which you say why in this case you have more strong correlations. And when this is the case, when you do an energy difference, you don't have any more error cancellations than you have DFT often. Think about it and then you tell me if you agree or not. Okay, so the idea is to use neural networks to approximate change in correlation energy. We know that this functional exists. Why do we know neural networks? Well, we use neural networks also because that the true functional is non-analytical, has several discontinuities, and that it's the best way to, it's a very good universal approximator, as shown by Korornik a long time ago. Okay, so we define, I'm towards the end of the talk, so please don't fall asleep right now. So, okay, so we use a meta-GGA architecture. So we have density, spin polarization, kinetic energy, reduced density gradient. In order to give stability, we have some information passing from the exchange and the correlation. So this is our neural network that defines our exchange and correlation potential. Very good. It's relatively small, much, much smaller than what DeepMind developed. So the hope is that we are smaller and more stable in terms of parameters. So now we need to describe, now we need to have in our training set the kind of chemistry that we want to describe. So we use water molecules, simple molecules, NH3, NO. But we need also to use transition metals that were never used before by DM21 or Nagai. Chromium hydride, iron oxide, copper fluoride. We, unlike DM21, we do optimize the density. So our density changes at every self-consistent cycle. And we impose that our density, that the density of our functional is the same as the density of couple cluster, CCSDT. We use atomization energies and adiabatic energy differences from experiment. So we want to describe the chemistry, which is the chemistry of bonding, chemistry of spin state transitions. So we give different values of spin states, of spin splittings. Adiabatic energy difference are also called spin splitting. C06 coefficient tells you how much static correlations you have. So again, we want to try to describe static and dynamic correlations. So we go from almost a single determinant case to more multi-configurational case. And we have different spin multiplicities in our training set. Okay, so what we do? Okay, so we have our training set. We have our guess inputs to your neural network. We define the neural network enhancement factor for the exchange and correlation. We use the Lagrange multipliers to apply a series of physical constraints. So we want, and this is something that was not done by DM21. So you need and this is what the second paper said, you're not teaching your model to learn the physics, you're teaching the model to just reproduce the data that you're giving. So we believe that giving physical constraints is important. And what we do, following the strategy by Nagai, so this is their idea, we define our exchange and correlation functional. So these are two neural, so it's a neural network that are defined, so the function is defined as a correction to R2 scan. Okay? So you start from R2 scan, and then you optimize your parameter in order to obtain the properties that you're looking for, so the properties that I mentioned before. So you compute the exchange and correlation energy, the potential, the effective potential, you go into the self-consistent loop. Okay, this is what we do. Why do we choose R2 scan? Well, we choose R2 scan because R2 scan is a very good exchange and correlation energy. So if you don't know what exchange and correlation energy you need to use for your properties, R2 scan cannot be wrong. So it's based on scan, a strongly constrained and approximating normal functional by Perdue, developed in 2015. A few years later, so during this time from 2015 to 2019, it was shown that he has several instabilities arising from the fact that he cannot describe densities that change very fast, divergence of derivatives at rapidly decreasing electron density. So the authors developed the regularized scan, in which they modified a few things. But the regularized scan, so corrected all the numerical instability. So never use scan, for example, if you have molecules. This we tried. It's not very accurate. So the regularized scan correct for this numerical instability. Then we have the revisited regularized scan. That's why it's called R2 scan. Uses the same corrections, but also restores some constraint that the exact functional should have. So that's why we use R2 scan, because we believe R2 scan is a well-behaved functional. So the loss function includes errors on the atomization energies, on the electronic density, and on the adiabatic energy differences. Okay, I don't think I will go to the end of the talk, but I would just like to show the results of this function. I have different versions of the functionals, but okay. Now it's a question of optimization problem. Now we need to optimize our function. We need to optimize the parameters of the neural network. How do we do it? Do we use genetic algorithms? Do we use gradients? So we cannot use gradients because the functional is non-analytical in parameter space. So for example, here it's B3-leap. B3-leap, you have, as I said before, you have a fraction of LDA, you have a fraction LDA correlation, you have a fraction of LDA exchange, and a fraction of Hartree-Fock. So if you plot this thing, which is the energy, as a function of the Hartree-Fock fraction of X, you see that depending on the number of self-consistent steps that you do, you can have very many discontinuities that decrease as you increase the number of self-consistent functionals, but they're still there. So in transition metal complexes, achieving a self-consistency with 20 or 30 steps, it's not feasible. Sometimes you need many steps, so which means that you cannot propagate your error in the self-consistent procedure, and you cannot use gradients. Okay, so the training algorithm that we used is called, it's a modified particle swarm optimization. So you want to find the solutions that you're looking for. So the parameter of neural networks are a swarm of particles. So these swarm of particles move around. So like a swarm of particles forages for resources. Now in our case, we have particles, and we want to optimize we want to find the global minimum. So it implements the idea of collective intelligence, meaning that your particles moves from time t to time t plus 1, and when it moves, you have several components. You have velocity and the position that are defined also in terms of the other particles. So when a particle moves, you also moves in such a way that it takes into account the best solution ever visited by the swarm, not the particle itself. Was it clear? Okay, so you moved your particles in such a way that you have some memory, some inertia, what is seen before, the particle and the best solution that the whole swarm has seen before. Then, in order to make sure that you are never sure if you are in the global minimum, of course, in order to minimize the probability on having local minima, we move our box around in order to find the solution. And we move the box in such a way that we center the searching box in the best solution ever found, and we reinitialize the particles. So particle 0, at the beginning, the particles are in R2 scan. Then we move around, meaning that the correction to R2 scan is looking for a solution. Okay, this is again the whole thing, but I won't talk about it. This is the optimization procedure in terms of migration. This is the Spearman correlation matrix that tells you step 32. So we have done different combinations of the training set, okay? This is the whole, all the molecules and quantities are in there, and you see, just instructive to see that the density is indeed helping your convergers, especially, so also for transition metal complexes, meaning that it is a density-driven error. Okay, so this is the table of results. Okay, so Nagai and Sugino functional is the first functional that I ever shown. This is the error computed on these molecules, on the adiabatic energy differences. PB is very wrong, error 1 eV. Scan, also very wrong. NAS, the Nagai-Sugino, wrong. DM21 starts to do better, not that bad. This is PB, you correct the density corrected scheme that uses the Hubbard U that I showed before. That was the best performer before this development. And now we see that our functional artificial neural network trained on all the molecules is the best performer, also compared with all the other different subsystems, sub-training. Okay, so here to show, okay, we are training a functional starting from R2Scan. But how far are we from R2Scan? Are we going back to R2Scan or really optimizing something? Well, iron oxide is a very difficult case. So, so here we have the pointwise integral of the density difference between pairs of functionals. And here you have local linear embedding that where distances just shows you how different these densities are. And we are indeed optimizing our functional. We are far from R2Scan, and we are close. This is our functional. We are close to coupled cluster, which is the thing that we want to optimize. Okay, interesting. But how does it perform in terms of other molecules? Other ions, nickel, manganese, things that the training hasn't seen before. Is it transferable, this functional? Or geometries that they haven't seen? Yes, it is very transferable, and we are the best performance compared to R2Scan, TPSS, PB, etc., etc. So we're very happy. Okay, I don't think I will go through these slides. I do have time, but it becomes a bit technical here. Okay, so we're very happy about this functional. So it can describe atomization energy, not just the adiabatic energy difference, many things. So you can use it for whenever you have a transition metal complex. But when, don't look at this figure for now, but when we used it to see whether we can apply it to very different kinds of small ions with different kinds of electronic correlations, we see that it was not that good as we hoped for. So we said, okay, look, we can do better. And the way to do better is to use adiabatic energy differences of ions. I want to go fast, but I want you to understand. So I try to find the right compromise. So these are adiabatic energy differences, different spin configuration, spin multiplicity. Okay, for different ions, these are just one ion, okay? Isoelectronic, charge 2+, 3+, 4+. So this is isoelectronic, this is isoelectronic, and so forth. So this is the NIST database. So these are experiments, which is not accessible anymore, if you know. So coupled cluster, as I said before, is not that good. CASPD2 is very good. We can reproduce exactly the adiabatic energy differences. And so what we claim and what people claim is that ions are very difficult to compute, are simple but among the most difficult. And one hypothesis is that because of strong static correlations. So our idea was to include these ions in the training set. And just to give you an idea why is DFT wrong again, if you compute this adiabatic energy difference using PBE, it's a complete mess. If you use restricted for low spin, you're very far. If you use the self-consistent minima, you get another solution. And if you look for hypersinglet, like your solutions like this, you get even far, so you get closer to the solution but farther from the other things. So PB is kind of not easy function. Okay, this is to show that the potential energy surface of I don't know if I want to explain this. So no, I won't explain this. Okay, so we trained a new functional with the same architecture, very similar, but just changing the physics that we give. So we still use the Lagrange multipliers, so the exact limits are maintained, but we just include more static correlation. We include molecules, a molecule for which we use the Caspity-Tooth energy and density, and a bunch of different delta E's for the ions. We train the functional, and okay, so the first good thing is that this is the second functional that we train, and this is the first that I showed before. When the second functional gets very close to the NIST database solution and gets correctly the hypersinglet, there is a kind of symmetry breaking that it's capable of doing. So in this case, we wanted to test the generality on larger data set. So we use published data sets. So these are the different molecules that I've shown so far. But there are also data sets of transition metal dimers, reaction transition metal barriers, and these are chemical reactions. And so the message here is that it's not that positive as we had hoped for. Because, so for the transition metal dimers, we are the best performers. We are the best performers for more, but also Tuscan is a very good performer, so we don't gain much. For transition metal barriers, PB0 is the best performer. And here, we are best performers for these complex molecules and this difficult situation, which are the ions. So the take-home message here is that we lose precision in some of the things that we know well how to compute. Here is the best performer. But we are more general. So we are never too wrong. Let's finish with this. So when you use this functional, you're not assured that it's the best performer, but you're sure that your error are substantially reduced in general. Okay. Thanks for your attention. So just to finish, so with this functional, so many thanks to João Paulo, who's a brilliant postdoc who worked on this topic. So all this development is done in PyTorch, and the functional is available. You can use it whenever you use PySCF. And if you're interested and you want to develop your own functional, you go to this webpage here, and you'll find tutorials, Jupyter Notebook, which explains you how to define the functional with PySCF. How to customize your functional. Here, these are the parameters of your functional. And here you can combine different functions of exact exchange, etc. Or different fraction of different functionals. Here it explains how write a perceptron as a functional. And there is no, I think there is we don't have the optimization of the functional program, but you have examples on how to write your functional as a neural network. And I'm done. You can ask questions.